Hello everybody and welcome back to your YouTube channel. In this video I will be covering the time complexity for the least squares regression problem. So before we actually do this, I'll take a while to tell you about the time complexity that is involved in a matrix multiplication operation. So given two matrices B and C of the order m times n and n times p, the product will be a matrix A of the dimensions m cross p, okay, and this multiplication operation, the multiplication of B with C, is going to proceed with the time complexity of order of m into n into p. So how are we going to compute the time complexity? We will simply be multiplying the outer dimensions with the inner dimension. So in this case the outer dimensions are m and p and the inner dimension is equal to n. So I will be multiplying m with p and finally with n, and that gives us the time complexity for this matrix multiplication as order of m into n into p, right? Now in case the matrices B and C happen to be square matrices, then all these values will be equal to each other. Let's assume that m is equal to n is equal to p, okay? So in this case, if we have two different matrices which are square, okay, or each of order n, then this same matrix multiplication operation is going to proceed with a time complexity of order of n cube, okay. Now apart from this naive implementation, we also have some faster implementations. For instance, if we talk about Solve-Strassen's algorithm, it is able to multiply two square matrices with a time complexity of order of n to the power 2.807, and as of now the fastest algorithm which is available is Coppersmith-Winograd algorithm. Why is it so popular? It is popular because it is able to multiply two different matrices with a time complexity of order of n to the power 2.37, right? And in case you are wondering, matrix multiplication of time complexity of order of n square does not exist as of now, okay. Now that we have learned about the time complexity which is involved in multiplying two different matrices, let us now shift our focus to computing the solution for the least squares regression. So as you already know that least squares regression has got a closed form solution which is given by beta gap, and that is equal to x transpose x whole inverse multiplied by x transpose y. So what are these quantities x and y? X here is your feature matrix of the dimensions m times n. What does it mean? It basically means that this feature matrix is going to have m samples and n number of features which are being used to represent each of those m samples. Similarly, y is our target vector, and that will be of the same dimension as the total number of samples, which is equal to m. Now, if we look at the computation of this least squares regression problem, the solution to this particular problem, different operations are involved. For instance, we have two multiplication operations where in the first operation we are multiplying x transpose with x, and in the second multiplication operation we are multiplying x transpose with y. Similarly, there is also an inverse computation algorithm taking place. Okay, what this algorithm is doing? This is computing the inverse of x transpose x. In addition to this inverse computation, we have another multiplication operation, and that comes into existence when we are multiplying this inverse term with x transpose y. Okay, so in general, if I were to summarize, the computation of solution to the least squares regression problem involves three multiplication operations and one inverse computation operation. Okay, with this, let us try to analyze each and every step and try to find out the time complexity of those steps. So the first step, you know that there's a matrix multiplication operation going on where we are multiplying x transpose with x. So you already know that x is your feature matrix of the order m times n. So that is why when we will be multiplying x transpose with x, the result would be a square matrix. Okay, so what would be the time complexity for the computation of x transpose x? That will be equal to n square m. And how am I getting these numbers? See, what we have to do is we simply have to multiply the outer dimensions with the inner dimensions. So the outer dimensions are n and n. So if I multiply these outer dimensions, the product would be n square, and this product will again be multiplied with the inner term. And what is that inner dimension? M. So the total time complexity for this matrix multiplication operation would be equal to order of n square into m. Okay, then there is another multiplication going on where we are multiplying x transpose with y. Okay, so x transpose is a matrix of the order n times m. Similarly, y is a target vector of dimensions m times 1. So if I were to multiply these two together, the time complexity involved would be of the dimension of the order m into n. Why am I getting m into n? I will be multiplying n with 1 and then finally with m. So n into 1 into m will be equal to order of mn. Okay, so this was the time complexity for the second multiplication operation, and the time complexity was order of mn. Likewise, there's a third operation going on, which is basically an inverse computation, where we are computing the inverse of x transpose x. So you already know that x transpose x will be a square matrix of the order n, and the inverse computation takes place in cubic time. So the time complexity for computing this inverse would be of the order n cube. Okay. Now coming back to the final operation, the final multiplication operation is involving the multiplication of the inverse term which was calculated earlier, okay, with x transpose y term. So this inverse term is having the dimensions n into n, while x transpose y is having the dimensions n into 1. Okay, so what I would suggest is that you pause this particular video and convince yourself of the dimensions that each of these terms is having. Okay, try to solve it yourself. Okay, now when we will be multiplying two different matrices, one of the order n into n and the other of the order n into 1, the time complexity involved would be order of n square 1. Okay. Now in this particular slide, what I have done is I have summarized all the four operations which are involved in computing the solution to the least squares regression problem. So as you can see, the first operation was multiplication of x transpose with x, which took order of n square times m time. Okay. Likewise, the second operation was the multiplication of x transpose with y, which had a time complexity of order of m into n. The third operation was basically computation of inverse, which was having a time complexity of order of n cube. And finally, there was a matrix multiplication operation going on, and which proceeded with the time complexity of order of n square. Okay. Now that we have found out the time complexity for the individual terms, what we can do is we can compute the overall time complexity. And the basic simple formula is that I will be adding up the time complexity of each of the individual steps. So that is, we will be adding the time complexity of step 1 through step 4. Okay, as is highlighted in equation 3. So once we do this, I will be getting something as represented by equation 4. So the overall time complexity for computation of solution to the least squares regression problem would be order of n square times m plus order of mn plus order of n cube plus order of n square. Okay, so these basic terms are basically the ones we have computed earlier. The terms for t1, t2, t3 and t4, those terms are put as such, and as such the equation 4 is formed. Now that we have the overall time complexity for this particular model, there are few points which are worth noting. For example, in any machine learning application, the total number of samples m will in general be greater than total number of features. That is, in most of the cases, the value of m will be greater than value of n. So what does it mean? It basically means that if I compare order of n square m with order of n cube, in most of the cases what I will be getting is that order of n square times m will be greater than order of n cube. Similarly, order of n square times m will again be greater than order of mn. And lastly, by the same logic, if I were to compare the order of mn with order of n square, what I will be getting is that order of mn will be greater than order of n square. Now the results are just coming because of the fact that in general m is greater than n. That is, the total number of samples are basically greater than n, the total number of features. Now what we do is we incorporate these changes, we incorporate these assumptions, and what are these facts? They're not assumptions, they are basically facts. The first fact is that order of n square m is greater than order of n cube. Then order of n square times m is greater than order of mn, and order of mn is again greater than order of n square. So let us try to find out what actually happens. So if you compare these two equations, the first term order of n square m is kept as such. The second term order of mn is again reflected in equation 5. Now let us try to look at the third term. Originally the third term was order of n cube. So what we have done is we have replaced this order of n cube term with order of n square m. Why is it so? Because In the presence of order of n square m term, order of n cube does not hold much significance. So that is why I can always replace this order of n cube term with order of n square term. Okay, and let us look at the fourth term. The fourth term was order of n square into m, that is order of n square. And because m is greater than n, I will be using the result which is highlighted by 0.3, and I will be replacing order of n square with order of mn. Okay, so I will again repeat what I have done. The first two terms I have copied as such. This third term, which was order of n cube, that has been replaced with order of n square m, because order of n square m is in general greater than order of n cube. Similarly, order of mn was greater than order of n square, so that is why the fourth term, which was order of n square, has been replaced by order of mn, as can be seen in equation 5. Now, I will be taking the results from equation 5. So what results we are getting? In the computation of overall time complexity, I am having two terms of order of n square m and two terms of order of mn, right? The same thing I have written here. This overall time complexity T is written as twice of order of n square m plus twice of order of mn. Now you already know that order of n square times m is always going to be greater than order of mn. So that is why in the presence of order of n square m term, I can always neglect this order of mn term. Okay, so once I do this, I will be obtaining the total time complexity for this entire problem as order of n square m. Okay, so this is the total time complexity for computing the solution to the least squares problem, that is equal to order of n square m. So what does it mean? It basically means that the time complexity is linear in the number of samples, which is equal to m, and this particular thing is quadratic in terms of the total number of features. Okay, so this brings us to the end of this particular lecture. I hope you have learned something new. In case you have learned something new, try to share this video among your friends. Thank you.